All right. So yesterday's we have stopped at somewhere here, right, regarding the rotational mechanical system. Okay, just a quick recap on what you have learned yesterday. Okay, what we did is we use for a two-dimensional system. Okay, translationally, right, we use to break them into two separate free body diagram, and we analyze such that for the first free body diagram, we assume that this object is moving and the other object is not moving. And the second situation is the other object is moving, but the main object in the free body diagram is not moving. Okay, then we superimpose them into a single free body diagram to form the equation of motions related to this particular mass itself, right? So from there, we can actually form two separate equation of motion for two separate masses, okay? And from there onwards, we can do some sort of simultaneous equations, or maybe in linear algebraic methods, we use Cramer rules to solve them systematically, right? So here we can see that everything is using the Cramer rules, right? So any questions related to the Cramer rules so far over here? Okay, so
No, doctor.
all right. So if no, then we will proceed with the second part, right, which is related to the rotational mechanical system. Okay. So basically, for a rotational mechanical system, the concept is exactly the same with the linear mechanical system. Okay, we still have a spring, we still have damper, and we have mass, right? The only difference is that instead of translational motions, okay, all these items, okay, for example, the spring, okay, they are actually in the rotational type of spring. Okay, so when you do a torsions, okay, then when you release it, then it will like twist back, okay, to the original positions. Okay, same thing with the dampers. Okay, so it is like a kind of bearing, okay, where it allows you to rotate, okay, but at the same time that you slow down your accelerations at the beginning. All right, so that will act as a damper. Okay, and the last part would be the mass. Okay, so this mass basically is referring to the moment of inertia, right? Inertia of the rotational system itself. Okay, so here we would refer to the J, right, instead of the I. Okay, rotational speed. Okay, so as you know, the torque is equals to the I alpha, right? Alpha is the angular accelerations, and this J or I is referring to the mass moment of inertia, right? So here is the relationship between the so-called the angular torque as well as the angular velocity, right? And similarly, you have the impedance, and the concept is very similar. Okay, once you understand how to form the equation of motions for for a rotational mechanical system, therefore you can easily use this impedance concept, right, to help you. Okay, so once here is an example, okay, where we can, I guess we can just directly use a impedance method. Okay, we just use directly with the so-called S, right? Okay, where here instead of using X, okay, previously we used X because we assume the movement is linear, okay, along the x-axis, okay, the x-axis. So here we would like to use a theta, all right, to represent the changes in terms of angle, okay, theta. Okay, so just assume a simple I would say single degree. Okay, probably yeah, 2 degree. All right. Even though this is a single shaft itself, okay, we assume it's a 2 degree of freedom system, probably, right? Where assuming this is a very long shaft, okay. So when you have a very long shaft, okay, so let's take this so-called ruler, okay, even though it's made of steel, okay, whenever one side is twisting, okay, so actually there is a twisting in between the the material. So you can see a twist over there, okay, even though it's very small, okay. So we can somehow assume that a very long shaft itself, okay, if it is made of some kind of material that are not super solid, okay, super stiff, I would say, all right. Therefore, they will behave like a spring, okay, where it will be some kind of delay in terms of response. Okay, so one side may turn, then the other side will slowly follows later on, right? So we will assume this kind of characteristic along a very long shaft itself being replaced with a spring. Okay, so this act as a spring coefficients over here. Okay, so and because of that we can assume that here there is a two bearing, okay, that act as the support, okay, of two ends of the shaft itself. Okay, so this bearing we assume that as a damper over here, okay, similar to the frictional force, right? So we assume that as a damper. Okay, so we have D1 and D2, okay, on the both side, even though this is the same shaft. Okay, this diagram I purposely put such that the diameter is different, right? So that you can see that actually there is two part, but it can be a single long shaft with the same diameter as well, right? So that depends on how you would like to define your system, right? So once we have separate this problem, okay, into two separate masses, okay, so you can assume that there is a moment of inertia, a J1 and J2, all right, being represented by here, right? So now we would like to start with something like this, okay? I guess very similar, okay? First thing, we assume the positive directions, okay? So positive direction is rotating in uh, anti-clockwise directions, right? Anti-clockwise directions, yeah, anti-clockwise directions, right? So what happened is what sorry, a clockwise direction. Okay, so whatever in the anti-clockwise directions we will assume as a negative probably here, right? So what we have over here is that the first thing occurs would be we can see the spring, okay, acting on the free body diagram. Probably put some remark over here first, okay. So we just look at this system first, right? Okay. So cutting over here, we can see a spring actions on the mass one. Okay, so this spring action is being translated by the K theta 1, okay, which always oppose the rotational directions, right? So we have K theta 1 over here. Okay, then what else is against the rotation? The damper. Okay, so for a damper we have a d1 s theta 1, right? So we have the second one, and the third one, what is occurring there is, as we know, for a linear side we would use the mass inertia, right? For here we would use the rotational moment of inertia, right? So we have the J, okay, J s square theta. Again, this will slow down the tendency to rotate at the beginning, right? The inertia of it. Okay, so again, against the direction of the rotation. So three items is over here, but what is the item that is in the same directions would be the T, okay, because we assuming that there is here we in this diagram we say that we apply a torque, okay, to turn this shaft at the j theta side, okay, j1 side, sorry, okay, j1 side. So we will have this torque, okay, as the external force, okay, to these rotations. Okay, so we complete the first part. Okay, on the second part would be on when this diagram is not moving, but the other diagram is moving. Okay, the other side is moving. Okay, so we can see that the other side is moving, then for sure it will turn this spring to rotate together in the clockwise directions. Okay, so that is being reflected by this red color, right? So this red color represents the effect for the second side, okay, the J2 side, okay, on the J1, okay, when the J2 is rotating. Okay, so we have the motions which is along the clockwise directions with the uh, impedance or values, okay, given by K theta 2, right, because it's due to the rotation of the second side, right, it's theta 2, right. So you can see that this diagram, once we have formed this diagram, so we can easily sum them up together. Okay, so total of all the terms equals to t, let's say. All right, so meaning to say t is positive. Okay, if you are not sure how to add them up, what you need to do is to just follow one side as a positive directions. Okay, add them up, everything equals to 0, then only you rearrange the side, right? So if let's say we assume here is anti-clockwise all positive. Okay, so we will have k1, okay, k1, okay, and d1s, okay, and then j1s square, okay, everything multiplied by theta 1, right, then minus ts, okay, you should put uh, minus ts over here, right? And then this one also minus, okay, minus k theta 2 over here. Okay, so once you have this equation equals to 0, you transfer this ts over the other side, so you would get these equations, right? So same thing or same methods, okay, we would apply the same concept for the second part of the of the shaft, I would say, all right? The J2 side. So when you assume the J2 side, again, you just cut through it. You have the uh, K2, okay? K2, yeah, K theta 2, sorry, okay? K theta 2. Okay. Now we consider this second part, right? Okay. So you have this K theta 2, okay? And then we have the D2, okay, D2S, okay, as well as the rotational moment of inertia related to the J2, okay. So three parts, okay, and then this is when the side number 2, the theta 2 is rotating, okay, where theta 1 is not rotating. Okay, now when theta 1 is rotating, theta 2 is not rotating, then the effect would be being represented by this, all right, which is yeah, along the directions of the theta 2 as well, right? So again, sum them up together equals to 0. You have two equations, equation number 1 and equation number 2. Okay, so again, using Cramer rules, okay, depending on what output you would like to form. Okay, if you would like to know the transfer functions, the relationship between the output, okay, I would say the output is theta 2. Okay, if that is the case, so it would be theta 2 divided by the input, which is the torque, right? You would want to know if I give certain torque, okay, so how it would be uh, responding on the other side. Okay, if the shaft is maybe 10-meter long, okay, if I put this torque, okay, how long it would reach the other side. Okay, if it is very short, then imaginally we can know that it's almost immediate. Okay, but if it is very long and the frictional force is very high, then whatever you turn over here may not be reflected directly on the other side. Okay, so this is where we would want to analyze the response, okay, on one side to the other. Okay, especially when the material of this particular shaft is not that stiff. Okay, the stiffness of it is not there, right? Therefore, probably if you come out with like a rubber type of a shaft, then the effect of K is even more there. Okay, you can see that what would happens in terms of the response, okay, when you apply some torque rotational over one side, okay, over a long distance, what would happen to the other side, okay, the theta 2 side. Okay, so if that is the case, then we would want to form this so-called transfer functions, okay, which is related to theta 2. Okay, so if it is related to theta 2, then for sure you would want to substitute into each other. Okay, remove the theta 1 and so on, right? So you just use the Cramer rules. Okay, so you should get the suitable so-called answers, okay, to form the for the transfer functions. Okay, so you may try on your own, okay, just to make sure that you can form this particular transfer function k over the determinant. Okay, so if you can get this, then should be fine. Okay, meaning to say from the derivation part until the solution part, okay, to form the transfer functions sections is doable now, right? So this would be tested, okay, in these courses, because as you know, the first course outcome would be to able to model, right, a mechanical system, right? So it can be either two-dimensional translational or rotational system. Okay, as long as you understand the concept, can build the free body diagram, form the equation of motions, there is marks. Okay, then after that you should able to identify what is the transfer function required. Okay, whether the questions or the needs is to define the relationship between the output at theta 2, or maybe sometimes they would like to see what happens to theta 1 or maybe theta 3 and so on, right? So it depends on what is the needs or the questions itself, right? So from there you have to form to identify what is the suitable transfer function. Okay, once you know this, then only you can solve this equation, rearrange them in a form that you have theta 2 as well as the input, right? So here is another relationship between the mechanical rotational system itself. Okay, I guess maybe probably you have seen this before in mechanics of machines, probably the courses, right, where you have relationships of gears and so on, right? So okay, so I assume all this you can always refer back, all right, on how to get the torque and theta relationships, okay, in between two uh, matching or meshing or mating gear, right? Okay, so okay, based on that particular concept, okay, we can always see that there is a relationship or a ratio, okay, between the gear, okay, between the gear, okay, N1, N2, and so on, all right? So what happens is that in a normal rotational system, okay, mechanically, okay, we would use a lot of gearing. Okay, the gearing itself can be a real gear or maybe a pulley itself. You have a timing belt type or maybe a flat V type of pulley. Okay, again, it still have the effect similar to the gear, right? It's still connecting two different or maybe more than two rotating shaft itself. Okay, therefore we would like to see in these sections, we would like to see the effect of the gearing on a mass spring damper system. Okay, so what we shown here is just a derivations, okay, what on what is actually happening, okay, during our derivations. Okay, basically this three diagram is the same diagram. Okay, the only difference is the first diagram, it shows that there is a gear, right? This is a gear symbol, right? So you have two mating gear over here, okay, and one mass spring damper system over here. Okay, so generally, if we would like to define, let's erase something first. Okay. So now let's just look at this particular section first. Okay, since we would like to see the effect on from the so-called motor side or the the other gearing side. Okay, first we would like to form this relationship first. All right, so this relationship is very straightforward. Okay, you can see that we have the inertial terms, the damper terms, and the spring terms. Okay, which is related to the torque. Okay, acting on this particular side. Right, so the equation is very straightforward. Okay, so once we have this particular so-called spring mass damper system equations, okay, to define this particular area, what next is that we would want to also include this particular sections, okay, the effect of the gearing. Okay, so how we can relate this is through all this relationship. Okay, we know that the torque, the gearing ratios, and yeah, the rotational angles are interconnected. Okay, so the relationship between the theta 2 and theta 1 can be given as this. Okay, you just refer back. Okay, theta 2, theta 1, okay, they are related to this. Okay, so we just substitute theta 2 relationship over here. Okay, so same thing. Okay, we can also find out what is the relationship between the torque, okay, on this shaft as well as the torque on the other side. Okay, so this is equals to this. Okay, so this is equivalent to this. Okay, so once we have this, okay, when we rearrange, okay, so you can see that this gear ratio and this gear ratio, okay, when we shift it up, it actually has this effect. Okay, the gear ratio to the power of 2. All right, so what are the benefits or the ideas behind all these things is that we can see the effect, okay, of the torque at this particular side, okay, on the first gear itself. Okay, torque number 1 will have a exponential effect, okay, on this gearing. Okay, it's not mainly the gear ratio, but it's a exponential effect, okay, on the whole system. Okay, on, so you can see that the n1 over n2 to the power of 2. Okay, so what happened here is that this t1 is what being supplied by probably a motor, right? Because you may put a motor over here with a gear, right? So how to get this T1? It is based on the spec of the motor, right? So once you get the spec of the motor, then immediately you can see how this whole system actually works. Okay, so you can see that actually all these things will have a effect of n1 over n2 to the power of 2. Okay, the kind of effect, okay, due to the gearing itself, right? So same thing, probably when we extend it longer, okay, to a bigger system, then it can be from one gear set or to two gear set, right? So if it is to the two gear set concept, the idea is very similar. Okay, uh, we would know that the effect is n the gear ratio to the power of 2. Okay, so what we need to do is we just identify and form in this particular format. Okay, so we have the inertial terms, okay, general format, okay, inertial terms as well as the damper term. Okay, normally the spring effect may not be there. Okay, but if you would like to include the gear effect, okay, you can also plus the gear effect over there. Sorry, the spring effect. Okay, the K. Okay, so generally we would simplify it into this so-called equivalent system. Okay, even though you may have more than one pair of gears or maybe 10 pairs of gears. Okay, so what we would do is we do so-called a reflected mass moment of inertia. Okay, so reflected means it's being transferred from one side to the other lah. Meaning to say, if something is happening the other side, okay, how it would be being reflect on the important sections. Okay, so the important sections over here probably would be on the motor side, right? The T side, okay, or maybe on the other end, okay, depending on what is the needs that you would like to model. Okay, so in this case, if the questions would like to see the relationship between the torque as well as the theta, okay, theta on the motor side, okay, then therefore we will reflect everything to here, okay, to this particular side, to the motor side. Okay, so when we reflect everything to the motor side, meaning to say we would use theta 1, okay, so we will use theta 1 over here, okay, as the output and the T as the input. Okay, so here what we need to do is we add them up. Okay, since it is being reflected on this side, meaning to say whatever J acting on this side is J. Okay, J1, right? So at side A, side word number 1 is J1. Okay, so after the gearing, okay, so this gearing itself is being reflected over here. Okay, it's due to the first pair of gears. Okay, so why J2 and J3? Because they are connected with the same shaft. Okay, so we will assume that let's change some color. Okay, we will assume this as one single item. Okay, now we simplify our problem. Okay, we don't go into detail in this way. Okay, we assume they are the same item now, right? So same item, what we do or simplify, we total them up together with the effect of n1 divided by n2 over here, right? Okay, so after that, same thing, we have J4 as well as maybe the load itself, okay, the items that you would like to turn. Okay, so this J load would be maybe a shaft or a turbine or a fan or whatever it is, right? So you have J4 and J5, okay, but how it is being reflected is that you have to multiply of N1, N2, okay, and then N3, N4, okay, output, input, okay, N3, N4, okay, to the power of square. Okay, so this is how you can reflect all the moment of inertia to the end. All right, because all these items will rotate somehow. Okay, and whenever it rotates, there is a rotating mass. Okay, that you have to consider. We call it mass moment of inertia. Okay, same thing for the reflected dampers effect. Okay, same thing, you would have D1. Okay, for those that are not given, then we just assume nothing there lah, right? So since only D1 and D2, we only consider D1, which is connected directly to the motor, and D2 we have to multiply by the ratio square, okay, because it's going through a pair of gears over here. Okay, so once we get this reflected moment of inertia as well as the damper side, okay, therefore we just substitute into our equations, okay, and rearrange it, we would get something like this. Okay, so this is how you can start to find out the equation of motion for a rotating system, okay, through gears and so on, right? So once you able to form this, okay, meaning to say later on, okay, in the futures, you will be able to analyze them first, okay, how fast it will respond. If let's say you give a certain torque to it, okay, the torque can be, because electrical motor as well, okay, if you give a current, it may not directly from zero jump to maybe 1000 rpm, okay, it will start from zero going to 1000 rpm maybe slowly. Okay, there is I would say a characteristic of the motor, okay, where it will start to ramp up and ramp down and so on. Okay, so all this effect will be taken into account, okay, to analyze, okay, or to control precisely, okay, on a particular system, okay, especially when the system is I would say uh, require precisions, okay. For example, nowadays that we probably long time back, you still can see CD-ROM, DVD-ROMs, okay, where internally, okay, there is actually a motors that control the positions of the reader, okay. So every time we send a electrical signal over there, we have to consider how fast it will respond, okay. It will not directly move, okay, at a certain speed that we would like, right? Okay, there is a certain time before it reach the maximum speed, okay, and all these things will be considered, okay, through this, okay, the control of the top or the top or maybe accelerations, okay, to relate them to the certain positions, okay. So all this would come into pictures, okay, when we would like to properly control a mechanical system, right? So on the other side, if you look into most of the control system book, okay, books written by for control system, mainly they are written for electrical engineers nowadays, because somehow they are easier to control, okay, instead of the mechanical side, okay. But we have on the mechanical, as a mechanical engineers, we also have to identify our scope, okay. We should know how to, what are the relationship between the gear and all these things, okay, so that we can assist the control engineer, which probably an electrical engineer who will do all this analysis later on, okay. If we able to model this system, okay, these transfer functions, we can supply these transfer functions for them to analyze probably, okay, in order for them to actually to control electromechanical system. Okay, so basically the I would say the relationship are very straightforward. I guess many differential equations books also quote this kind of examples from mechanical system and also electrical system. Okay, they are analogies. Okay, you have a capacity, resistor, inductors. Okay, and you can always use Kirchhoff law. Okay, when it flows through it, okay, we can form the kind of transfer functions. Again, this is more on the electrical side, where they would want to analyze if we supply a certain voltage, okay, how fast it will go through all these resistor, inductors, okay, to take into immediate effect, okay, so that your motor will operate also and so on, okay. This is on the electrical side or electronically control side, okay. So therefore, mathematically is similar, right? So I may not go through in details on this Kirchhoff or maybe mesh analysis. Okay, I guess you have learned this in circuit. Okay, uh, yeah, electrical, electrical subject probably. I forgot the name, right? The basic idea of all these things. Okay, and how they may related later on. Okay, so you can see that here is the electrical side, okay, and here is the mechanical side, okay, that you are going to model, okay. So here is the mechanical side that you are going to model. All right, so from there we can always so-called separate them together or combine them together into multiple block diagrams later on, okay, which we will cover soon, okay, after this, right? So any questions so far?
No, doctor.
Okay, right. So if no, then I will shift slide now. Okay, and Okay, the screen is on now. Right. So next part is on the block diagrams. Okay, after all those hard work to form the transfer function. Okay, and you can see that we have motor transfer functions, we have also the mechanical systems transfer function, and so on, right? So when we combine them together, we need some methods to actually combine them properly so that they can actually, even though it's visually yeah, be represented by blocks, okay, they can easily being combined, okay, into a simpler blocks, right? So the second objective of this cost outcome would be, after you model the mechanical system, you would like to simplify them as well, okay, block diagram simplifications. Okay, so here again, we just go through some concept, okay, that may be present in those textbook. Okay, they may say that they are classical approach, they are modern approach. Okay, so mainly, the classical approach relies on the frequency domain, whereas the modern approach, they use the time domain immediately. Okay, time domain immediately. So here we again use the classical methods, okay, as the basic concept of all this control engineering analysis and design later on. Okay, where most of the time we convert all these differential equation into transfer functions. Okay, so there onwards, we would like to generate the models and analyze them in the form of frequency, like the S domain, so called. All right. So the advantages would be yeah, stabilities. You can form a transient response. Okay, and other observations that are required for the design. Okay, the only thing is that you you have to convert it in terms of the frequency domains, okay, which may not be easily for you to visualize, okay, in terms of frequency. Okay, so the disadvantages would be limited to a certain range, okay, mainly for a linear system and the time invariant system. Okay, when in the future, okay, maybe if you would like to further into the advanced type of control engineering or feedback control system, then later on you can slowly move into the modern approach, like the time domain approach, where we do not go through those frequency domain, the S domain. Okay, we directly solve in using the time variables directly. Okay, which we will not cover in this course. Right. So this course will provide you the fundamentals, okay, required for the control engineering, okay, but may not go into depths in the advanced type, right? So generally for multiple system, we can represent those system using two methods. Okay, here our course objective is block diagram. Okay, there are another methods would be using the signal flow graph, right, which I again may not cover it, right? My focus would be to simplify your study path. Okay, I will teach most of the thing that you will use. Okay, in the subsequent chapters. Okay, signal flow graph. Uh, I may not cover it because in the later part we may not use it, okay, unless I cover another technique, okay, which you apply it, okay, using the signal flow graph. Okay, so our main focus would be the block diagram, okay, which is for the frequency domain analysis as well as design. Okay? When we draw the block diagram, is like the basic of statics or dynamics, okay, drawing the free body diagram, right? So in control, you have to draw a block diagram. And what is the block diagram is you first have to get the equations, okay, for the dynamic uh, characteristic of the component itself, okay, the gearing systems or maybe the motor system as well as whatever it is, lah, right? Take Laplace transform, okay, and represent into the Laplace transform equations, okay, and form into a block. All right, that's all. Okay? Then after that, you just connect them or assemble them into multiple elements to form a complete type of block diagrams. Okay, so this is a simple block diagram. We have the input, output, and the system that you have seen previously. Okay, you have seen this inside is a kind of fractions. Okay, that fractions represent the transfer functions. Okay, that give you the relationship or the ratio between the output always on the upper side, and the input on the lower side, the determinant denominators sections. Okay, so now we can how we can simplify all this block diagram is that uh, we will see the path, okay, how or the signal. Here I will use the word signal again, okay, similar to the maybe electrical terms. Okay, the signal referring to the directions of or the sequence of the process itself. Okay, I would say the sequence of the process. Okay, following the signal operations. Okay, so you go from one side, okay, to the other side and maybe come back. Right. So here uh, we have the signal operations. Okay, to show the directions or the sequence. Okay? And all these things, all this signal, okay, represented by the arrows itself, can come to a point where you can add or subtract. Okay, you can do some operations over there. Okay, so this operation actually when you do plus or minus, you are actually doing a comparisons. Okay, if you use value A, you minus with value B, meaning to say you are doing a comparison between A and B. Okay, A values may be 10, B values may be 8. Okay, when you minus it, you get 2. That 2 represent uh, the difference between these two values, right? You are comparing it. Okay, so we say a comparison components. Okay, so we would use a summing junctions. Okay, just a circle where you see a plus plus or minus. Okay, not necessarily in this sequence. It can be minus, plus, minus, or whatever it is. Okay, just to show what how this signal coming in will somehow do the operations. Okay, if it is plus, meaning to say at this point whatever comes in from C you will add into it. Okay, whatever comes from B you will minus it. Okay, whatever comes from R you will plus it. Okay, and where is the out? Okay, all these three arrow is coming in, right? So meaning you do the operation over here from all these three signal, sum them up. Okay, and the output would be E. So here we could represent this diagram as E equals to plus C plus R minus B. Okay, so this is a simple operations that you can see from the diagram itself. All right. The second type of diagram or arrows flow or signal operations would be a pick off or branching point. Okay, where you go to one point and you split into multiple points. Okay, when you split, meaning to say this signal will have the equal values and split into three separate operations. Right, so the value would be same lah, R. Okay, regardless of how many branches you have. Okay, so here is again the block diagram that you have seen, I guess, in the first slide. Okay, first lecture. Okay, where this is the co- common component of a block diagram where you have input, system, output, and then you can see that there is a summing junction here, right? So one is plus, one is minus, meaning to say you are doing comparisons, and once you do a comparisons here, we will have this ES over here. Okay, ES here normally we in control, we would call this E because it represent error. Okay, error, error signal. Okay, ERROR. All right, because why we say error is that the same signal goes in initially. Okay, after it processed through the system, it may give you, let's say you input 1. Okay, after you process you get 10. Okay, so it goes back over here. 10, we like we do a sensor, we check it out. Okay, so 10, when we minus it, then we have minus 9. Okay, so this is the difference between them. We call this as an error. Okay, and the system now will put 9 to do the correction, so that at the end of the day, okay, the output would match what we intend to input over there, right? Next operations would be what we call a cascade system, okay, where when we have multiple blocks, okay, and when we cascade them in a series, okay, we have G1, G2, G3, okay. What we can do is that, as you can see the signal flow, okay, the response signal R, okay, when we multiply by this transfer function, we get the output as GR, right? So when we multiply by the second transfer function, we have G2, G1R, okay? When we multiply by the third transfer function, we have the G3, G2, G1R, right? So you immediately from this kind of concept, we can actually simplify and group all these things together, okay, into single block, right? We say simplify into a single block, right? So what is the single block is that if we input R, as we know, R multiplied by this give you the output, right? And the output is G3, G2, G1, okay? Basically, you just have to multiply all these transfer functions together into one, right? So when you multiply all this together, the input multiplied by these transfer functions will give you the same output, okay, as you separate them into the cascade series of block diagram, right? The second type of system, yeah, yeah, block diagram systems would be the parallel system. Okay, you can see that this is a conventional parallel system. Again, you have G1, G2, G3, okay, which represent different type of transfer functions. Okay, as we know, when this signal R going through this peak off point, okay, meaning to say here is also R, right? Same signal. Here is also R, and this side as well is an R. Okay, so once we have 3R, right? So R multiplied by G1, you get G1R. Okay, same thing, G2R, G3R. Okay, and when we combine them together, okay, again, when we combine them together, now this is important. Okay, whether it is plus, plus, minus, or minus, plus, minus, or whatever it is. Okay, so this will determine what type of operations you would put later on inside your transfer functions. Okay, at the end of this simplification, you can see that it depends on these operations over here. Okay, if this is plus, the second one is plus, the third one is minus, then you have this, okay, G1 plus G2 minus G3. Okay, and this is our simplified transfer functions, okay, to represent this whole parallel system. Okay, so that whenever this input multiply by this will give us this exactly the same kind of effect in terms of signal, right? So once we are familiar with those things, now we move to the another form. We call it as a feedback system format, right? So this feedback system format is very common, okay, that you would see in control, okay, because in control, as you know, at the beginning we said there is open loop and there is closed loop control system, okay. So if it is open loop, then you would never check what is actual, right? You just turn on the current, okay, or you turn on the fan will rotate, That's it. Okay, whether it rotating at the correct speed or not, we don't care. Okay, that is open loop. Okay, when we would like to know the exact speed, okay, and increase accordingly, okay, so that we can control the speed of the fan, then that kind of system is a feedback or a closed loop type of control system. Okay, so in that case, you will see a line coming back. Okay, this is a signal gathered from maybe a sensors. Okay, coming back to to act as an input over here. Right, so we have the input transducer, the output transducer. Okay, from this. Okay, why we need transducer is because, for example, if you put a sensor over here, okay, sensors normally they are in the form of microampere. Okay, very small signal. Okay, microampere, so you need to amplify it, okay, to a kind of a signal that are suitable to be feedback to our controller. Okay, maybe in microampere you may want to increase it to ampere. Okay, so that it is being recorded, or maybe you have to transform it into a form of maybe if it is digital, then you may want to transform it into the bit signal, right? Okay, 1001 to represent what is the kind of values, okay, to be inserted back to the controller, right? So same thing with the input. Again, the input can be in the form of button, it can be in the form of uh, button, smartphone, or whatever it is. Okay, from there, that kind of signal again is very small. Okay, it can be just small ampere. Then you need a transducer to increase that kind of signal so that they are matching. Okay, before you send them to the controller. Okay, and that controller will control the plant. And this controller is the one that we intend to design later on, right? We have the PID controller, right, or P controller, and so on, okay, to control that particular system. Okay, so from here, okay, basically, if we see this is a cascade one, we can combine it, right? So this is the H, this is a plant, right? When this combined together, we just assume this is an R, right? Okay, so we simplify everything, okay, and in this form now, we normally can also further simplify into this. Okay, so this depends on the plus minus over here. Okay, if the feedback is minus, okay, you put the signal and come back, you minus the signal. Okay, so the block diagram will now become G divided by 1 plus. Okay, if it is minus, we use plus GH, GH, right? So this transfer function multiplied by the bottom, okay, GH, 1 plus GH, okay, G divided by 1 plus GH. If we are using the kind of positive feedback, okay, plus sign, then this transfer function will become G divided by 1 minus GH, right? So you just have to memorize these simplified transfer functions to represent this kind of feedback system. Okay, you will be able to summarize or simplify this this kind of looping type of flow into this, right? Okay. So next would be on the feedback derivations. Okay, how we can actually get this value. Okay, G over 1 plus GH. Okay, basically we follow these derivations. Okay, we have seen input, error, output, and the feedback signal. Okay, feedback signal. So here, if we would like to deduce it, okay, first we form the ratio between the output and the error. Okay, output and error. Okay, so it's Y divided by E. Okay, give us G. Okay, then at the same time we also put another ratio, which is the feedback and the output. Okay, feedback and the output give us H. Okay, so once we have seen that, now we look into the loop itself. Okay, this black color line. Okay, assuming the gray color signal now. Okay, so in this line itself, it starts from E. Okay, it ends with B, right? So in this line itself, okay, this signal will flow to the output, as well as this signal will flow through these two transfer functions, right? So when it flows through these two transfer functions, basically this G and H, you can total that up together, right? G and H. So the relationship between the B and the E, B and E equals to G multiplied by H, because this is cascade series type of system, right? Assuming this is disappearing, right? So we form this kind of relationship, right? So once we have the three relationship now, okay, 1, 2, and 3. Okay, so now what we can do next would be, if, okay, the transfer functions is a unity. When we say a unity value, is equals to 1. Okay, if it is 1, then very straightforward, the y and the b is equals. Okay, because this transfer function is 1. Okay, they are matching. Okay, if other than that, then you have to uh, use something like this, right? So now how we can actually combine them together is, in order to obtain the overall, we would obtain the ratio between the output signal and the input signal now. Okay, output and the input. Okay, so first we would have this arrow. Okay, arrow. Okay, and this is given by r minus b. Okay, so using equation number 2 previously, okay, substitute the b as such. Okay, substitute it as such. Okay, and then replace the error adjustment signal. Okay, we use this e. Okay, replace with this. Okay, so e replace with this. Okay, because we can rearrange here, right? So e move here, this move here, so it's y over g over here. Okay, replace with this. Okay, this one replace with this. Okay, b again, b equals to h over h multiplied by y. Okay, replace, rearrange. So finally we obtain this equation. Okay, which is g divided by 1 plus gh. Okay, if this is minus. Okay, if this is positive, then this would be become minus. Okay, this is how we derive the feedback system. Okay, and these transfer functions, we call it as a closed loop transfer function. Okay, closed loop transfer function, you can see the looping over there. All right, the next one would be how we can assemble them into block diagrams. Okay, so here sometimes when we try to simplify it, okay, it may not that straightforward. Okay, it may require us to move certain block before or after a certain points. Okay, so that you can form the familiar form, like the cascade, the parallel forms, okay, or the closed loop form itself. Okay, so here is one of the examples how you can actually shift it. Okay, so if you have a block diagram over here, and the summing junctions is on the left hand side. Okay, on the left hand side, if you would like to move it on before the summing junction, is it is possible. Okay, so this is our main purpose, okay, to rearrange, okay, that you would see the benefits later on, right? So how we can move this over there is that we will form an equivalent diagram over there. Okay, so if you intend to move this block diagram to before the summing junctions, what you need to do is, instead of adding only the transfer functions that you move before the summing junction, you have to add another uh, similar transfer function block diagram, okay, to the feedback side. Okay, so that when this two, okay, RG, okay, so when this signal come here, it will become RG, right? This signal X come here will become XG. Okay, so RG minus XG, okay, is our output. Okay, RG minus XG. Okay, so this would be the output. Okay, how it would be equivalent to this is that you can see that this is R minus X. Okay, this arrow will be R minus X. Okay, multiplied by G, so the output will be R minus X G, meaning to say this is Rg minus Xg, which is equivalent to this. Okay, that's why when we move this block over there to the left hand side of the summing junction, we also need to add another block of G at the bottom, okay, to the feedback side of the signal, right? Then another situation is sometimes it is before and we would like to move it in, okay, to the right hand side, okay, so that maybe you can see that here is a kind of feedback loop that you can form the equations later on. Okay, so you may want to shift it here. Okay, so if you like to shift it here, okay, what you need to do is you can shift it here, but in these sections you have to use 1 divided by G, okay, to reduce the effect of this G at this particular section before it is being shifted, right? So have to get all this relationship correct, right? Okay, so another examples, probably this from the textbook NIS, okay, Professor NIS, where sometimes in this form you would like to move it out over here. Okay, so if you would like to move it out over here, what you need to do is the other side you have to do a derivation 1 over G. Okay, how to identify all these things? Okay, if somehow in the exam or test, okay, or someday you forgot all these things, how you would see the logic behind it is that you have to write down the signal. Okay, this is R, this is RG, this is R, this is R, right, as the output. Okay, R going through this, you have to multiply by G, so you get RG, right? So going here, you have R, over here you have R, right? So the logic here would be this must not be changed, right? So this remain the same, okay? So if you intend to move it over here, so what you get would be R multiplied by G at this particular point, okay? So you have RG over here now, okay? So this RG going this line is correct, okay? But RG going this line, if you do not multiply by this 1 over G, you will get Rg. So that's why you have to multiply by 1 over G to remove the G, the transfer function over here, so that you get the R. Okay. So same thing if you want to move it in, okay, you cannot simply move one block. Okay, you have to move to all the parallel line. Okay, so that the effect is the same. Right. Here is an examples of a block diagram that you may see in the future, okay, or maybe in the some exercise, okay, where you would like to take practice, right? So you can see that very straightforward, that you can see somehow there is a lot of feedback loop. Okay, one loop, two loops, okay, and the third loop, right? So but before we do all this looping, okay, we solve part by part. Okay? So we solve part by part and okay. So we solve part by part. We will do the summation of this first, okay? Before we see the first feedback loop, okay? Combine them together into one, then another feedback loop, and the third one. Okay, another way is we can see that this one point is split into three, right? Parallel. Okay, so meaning to say this is a parallel form and this is a cascade form. Okay, so again, if you know the rules, then immediately you can simplify them together, okay, as such. Okay, so here is one of the way, right? So you would like to see the cascade, okay? So if it is cascade, you just multiply them together, right? Then on this side would be the parallel, right? Parallel form of system, okay? And the idea here would be minus plus minus. So you should get minus plus minus, okay? Minus plus minus to be correct, all right? Okay, but the only difference here, why in this example they don't use minus plus minus, they use plus minus plus. Okay, the opposite is because this is in the feedback bottom side, right? So if we intend to assign a minus sign over here, okay, then we have to use the plus minus plus. Okay, if we intend to use a positive sign over here, then we just have to use minus plus minus. Okay, minus plus minus over here, right? So is it clear over here?
Yes, doctor.
Okay, it's great. Right, so once you see this, okay, what you need to do is, this is another form of feedback loop, right? Feedback loop itself. Okay, so what you can do is you just apply the g divide by 1. Okay, since if I use plus over here, then this should be minus the g, and the bottom side is the h, right? Okay, so we can simplify into this particular form, right? And then we have a g1 over here at the outside. Okay, g1 over here, you just have to cascade it with the transfer function again. Okay, meaning to say you will have this g1, okay, and then go into the this format, okay, right? So approach, you just do the cascade, means you just multiply in again. So therefore you can see that instead of g2 g3, it has a g1 g2 g3 now, right? And this is the final simplified transfer function. Okay, so this is how you can see a very complex transfer functions, multiples of them, you can group them into at the end a single block. Okay, another examples here, you can see that yeah, it's now become a little bit more complicated. Okay, but no exact rules. Okay, as long as you can see the patterns, you just form simplify it first. Okay, so here is a lot of lines going here and there, right? So whenever you see a line something like this, okay, a line split out like this, okay, what kind of transfer functions over here? You have to assign a transfer function over here. Okay, don't forget. Okay, because later on you may somehow forget to assign a transfer function, and you neglect the effect of it. So the transfer functions over here is that if there is a signal line, okay, a signal line without a block, meaning to say the transfer function is 1. Okay, the values come here, multiply by 1, that's it. Okay, so you have to keep in mind that there is a block over there, 1, okay, to helps you. Okay, so based on that concept, right, so you may just follow these ideas, okay, from the books, okay, where you may first identify here is a feedback loop, okay, a feedback loop, okay, so simplify as a feedback, okay, and then from this point you can move it over here, okay, so that it form in this way. Okay, you can see that when you move it here, then you may see that they actually have a 1 over there, okay, or this one move to the other side. Okay, if you move this out, okay, then this line you have to do 1 divided by g2, right? So after that, combine these two together, Okay, you may see that this and this, sorry, this and this, okay, is parallel. Okay, again, this is a straight line without anything, but you can see is there is a transfer function 1. Okay, therefore you have 1 plus this one, okay, to form this particular transfer function. Okay, then the remaining would be you can see that this is a feedback loop. Okay, yeah, feedback loop over here. Probably you can see, okay, maybe you can combine these two together first. Okay, so you can see that this is the G1 G2, combine them together and there is a feedback loop later on. Okay, so again you can combine, okay, cascade, combine, okay, feedback loop, combine, okay, and then these two feedback loop, yeah, combine, yeah, combine, and then after this is a so-called cascade, okay, combine, right? So eventually you will see a wonderful magic over there, right? You can see a very so-called complex functions over there. Okay, that's why usually all those transfer functions, they just represent by G1, G2, G3, and so on, instead of writing the the full transfer functions, because you may do a lot of operations over here and there, okay, before you finalize with the final block diagrams. Okay, so I guess probably these rules, okay, uh, may apply. Okay, very similar to what we have described previously. Okay, if you are not sure, just test on your own. Okay, basically we have learned this previously just now. All right, just now how we can shift a block from before to after and so on. So just in a different form of presentations only, right? Okay, so I think that's all for today. Okay, the remaining we will cover it in the coming lecture in the next week Thursday. Right. So any questions before we stop?
No, Doctor.
No, doctor.
Okay. All right. So if no, then that's all for today. Uh, yeah. Okay. If you have any questions, do not hesitate to us in the group or maybe the Google Classroom. All right. So see you again. Bye bye.
Thank
Thank
you,
you, doctor.
Doctor.
Thank you, doctor.
Thank you, doctor.